So this lecture is about first order logic with data types. First, let's extend universal and existential quantifications in the presence of data types. So previously, the definition of propositions looked like for all x a and existential x a. So we were dealing with pure first order logic where the data type for these term variables are not specified. So this term variable can assume any term. But now we are going to extend this universal quantification and existential quantification with data types. So instead of this one, we will be using for all x in data type tau with this property A. And we decided to use these parentheses to indicate the presence of this term variable x inside proposition A. So this is the new notation for universal quantification. And similarly, we extend the existential quantification with this data type tau with A of x. So these term variables x in the universal and existential quantifications are bound variables. So if you want, you can rename these bound variables so that there arises no name clash. So let's first reformulate the introduction and elimination rules for these universal and existential quantifications. First, universal quantification introduction rule. So the question is, how do we So the question is, how do we prove for all x in data type tau, A of x true? So this will be universal introduction rule. And the idea is we assume that x has data type tau, and then we deduce A of x is true. That's all. And now this is a judgment. This is judgment. So therefore, we may use a hypothesis to state that this is an assumption. So therefore, we can use this notation, horizontal bar, to indicate that this is an assumption. So this is the for all introduction rule, where we use this data type binding. So this for introduction rule is, let's assume that x has data type tau, and then we prove A of x is true. Then we can deduce this universal quantification is true. So in comparison with the previous for introduction rule, which looks like this one, for all x, A true, we introduce a term parameter. We introduce term parameter A, and then we deduce this judgment is true. So this is the previous for introduction rule. So in comparison with this previous inference rule, now we no longer use term parameter A, simply because now we can directly use this hypothesis. That is, by taking advantage of this new form of judgment, the need for this term variable is eliminated. So we no longer use term parameter in the for all introduction rule. Okay, there's no term parameter. That's for introduction rule. What about for all elimination rule? For elimination rule starts with this judgment. For all x in data type tau, a of x is true. And the question is, how can we exploit this existing judgment? This will be for all elimination rule. And this judgment says, this judgment requires a term of a specific data type tau. So in order to exploit this judgment, you have to provide a concrete term of specific data type tau, because you cannot actually substitute an arbitrary term of an arbitrary data type for this term variable x. You have to provide a term t of a specific data type tau that matches the data type specified here. Now we combine this judgment and this judgment and prove that a of t is true. Put simply, this judgment says every term of data type tau satisfies a of x, and we know that term t has data type tau. Therefore, we can deduce a of t is true. So this is for elimination rule. Now let's discuss existential introduction rule. The question is, how can we prove existential x data type tau a of x is true? This is existential introduction rule. And this judgment literally says there exists a term x of data type tau such that a of x is true. So in order to prove this judgment in constructive setting, you have to actually provide a concrete witness t of data type tau, because that's what is required of this judgment. So you try to find a concrete term t of data type tau, and then show that this term t indeed satisfies this property A. Now, you have literally found a term t of data type tau such that A of t is true. So therefore, you have found such a term x here. So this is the existential introduction rule. Finally, let's consider existential elimination rule. Existential elimination rule starts with this judgment. And the question is, how can we existential elimination? How can we exploit this existing judgment? Remember that in the previous formulation of a personal logic without data types, the elimination looked like we introduce a parameter A. So this is existential elimination rule A. We introduce a fresh term parameter A, and also we assume that A is true where x is replaced by A, and this hypothesis is labeled with W. So every time you apply this existential elimination rule, you had to introduce this fresh term parameter A. Now, we can eliminate the need for such a term parameter here because we can directly use this judgment. So in comparison with the previous existential elimination rule, we no longer use this term parameter. This is gone. So this for all existential elimination rule is, we know that there exists term x of data type tau such that A of x is true. So let's assume that the term is actually x. and it has a data type tau, then we know that A over X is true, because that's precisely what is guaranteed by this existing judgment. And this is a new hypothesis, so we label it, for example, with a W. And we exploited these two hypotheses and then deduce C true. Then we can always deduce C true. So this is the existential elimination rule, where we no longer use the this term parameter. So essentially, there is no difference from the previous inference rules, except that now we specify the data type for every term variable. And thanks to the use of these new form of judgments, we can eliminate term parameters. So the annoying term parameters are gone in this new formulation. So we have introduction rule, elimination rule for universal quantification, and we have introduction rule and elimination rule for these existential quantifications. Now let's repeat the usual exercise. First, introduce the proof terms, and then we can talk about these beta reductions and the eta expansions. So what about the proof terms? So suppose that we assign proof term m to the proof of this a of x. So now this 2 is gone, and we instead use this proof term. Then the question is, what kind of proof term would you assign to the conclusion? So this 2 keyword is gone, and the question is, what is the proof term? So we decided to reuse the same lambda abstraction as the proof term for this for quantification. So now we have lambda x of data type tau, and the body of this lambda abstraction is going to be m. So now we lose nothing. From the premise, we have this term variable x and data type tau and proof term m, all of which are found in the proof term here. Term variable x, data type tau, and proof term m. So this is the proof term that we can assign to these universal quantifications. So proof term m now has lambda x data type tau over m. What about this universal elimination rule? For all elimination rule. So suppose that we have proof term m of data type, proof term of type this type. And here we already have term. And the question is, what kind of proof term can we assign to the conclusion here of type A of t? And we decided to reuse the usual notation for lambda application. So we can think of it as applying the function from m to argument t. So now we have m applied to t. So it's almost like the previous lambda form, for example, lambda x a of m, and m applied to another proof term m. The difference is this time we deal with terms instead of proof terms. So the binding here is about data types. Here the binding is about types, but here the binding is data types. But essentially there's no difference between these two in the sense that they both represent some sort of functions which takes an argument and returns something new. And now let's talk about the proof terms for this existential quantification. So suppose that we have a proof term M of type A of T. So this is now gone. And the question is, what kind of proof term would you assign to the conclusion, which should have this type? And we decided to use this construct that looks like a pair. So we pair these two things up, concrete witness T and its proof. So this is the proof term of type is existential type. And what about here? This existential elimination rule. So suppose that we have a proof term M of this type. So now this true keyword is gone. So we have now proof term M of this type. And here, this hypothesis is already annotated with this term variable. Now we assume that A of x is true, and we use this label W to represent the proof of this judgment. So that is, we use this W as a proof term of type A of x. And let's assume that we have found a proof term N of type C. So of course, inside this proof term N, we may see occurrences of this term variable x and also ordinary variable W. And now the final question is, what kind of a proof term would you assign in the conclusion, which should have type C? So now this is gone. And we use this familiar notation, let construct. So let's assume that proof term M gives us a concrete witness X and its proof W. So in general, we don't know what the proof actually is or what the proof term actually is. So the best thing we can do here is to assume that it is something. So we use this term variable W. And in general, we don't know the concrete witness, so we just say that the witness is X. And then we proceed to compute this proof term N. So perhaps that's the best way to interpret this new proof term. So there's nothing new, actually. We just rediscovered the proof terms that we developed in the previous discussion. So now proof terms M has this pair for existential introduction and this left binding XW M in N. Okay. So now we have developed this introduction rule, elimination rule, and also proof terms for universal quantification and the introduction, elimination for existential quantification, along with their proof terms. So now let's talk about the beta reductions and beta expansion. It's straightforward to derive this beta and eta expander stuff. The story is the same. For example, for beta reductions, you have detour. This is intro followed by elim, and the question is how can we get rid of this one? So let's just directly work with proof terms. So first, for all universal quantification. So the introduction form generates this lambda abstraction lambda x data type tau of m. This corresponds to for all introduction rule. And let's apply for all elimination rule right away. So you provide the term t. The question is, how can we reduce this proof term? And it's pretty easy to see that you can just substitute t for term variable x inside m, and you can show that these two proof terms have the same same type. So that's the beta reduction. What about eta expansion? Assume that you have a proof term of this for all type, for x tau a of x. And the question is, how can we beta expand it? By deconstructing and then rebuilding it. So intuitively, this represents a function. So we intentionally introduce this variable, term variable of data type tau, and then apply the function m to this argument. Then we can show that intuitively, the function represented by m is semantically equivalent to this new function. So that's the eta expansion for all quantification. And what about the existential quantification? The introduction form of existential quantification is this pair, term t and proof term m. So this comes from existential introduction rule. So for example, this could be for so it could have type existential x, data type tau of a of x. So t is witness, and m is the proof that the witness satisfies this property A. Now this is the existential introduction rule. And what about the existential elimination rule? It is lab binding. So let's assume that from this proof term, we have witness X and proof W. And we don't know what they are, so we just use variables. And then we proceeded to compute another proof term N. So this lab binding comes from existential elimination rule. And the question is, how can we beta reduce it? So the idea is pretty simple. Inside this proof term N, we may see instances of term variable x as well as term variable x and also ordinary variable w. And you just substitute t for x and n for w. So that gives us x, t, and for w we have n. So that's the beta reduction for this existential quantification. And what about eta expansion? In the case of eta expansion, we start with a proof term of this existential type. So how can we eta expand it? So we just destruct this one and then rebuild it by exploiting this lab binding. So let's assume that the concrete, let's assume that the witness is x and the proof is w in proof term n. Then we just rebuild the pair in this way. So that's all. So we have finished developing, reformulating the firstorder logic using data types. So we have just finished reformulating everything using data types. So the second part of the lecture is about natural deduction for predicates on terms. Natural deduction for predicates on terms. So far, we have used this principle of natural deduction extensively. So we use this natural deduction, for example, to define logical connectives. from proposition logic, such as implication, conjunction, and disjunction, and so on. So we can explain the meaning of these logic connectives based on the principle of natural deduction. And then we also used this natural deduction to explain the meaning of first order quantifiers. First order quantifiers, like for all x data type tau and existential x data type tau. Now we can explain the meaning of these quantifiers using natural deduction. And we also used the principle for natural deduction to define data types, starting with these general data types such as this function type and product type and sum type and so on. So we can explain the meaning of these data types using natural deduction. And we also applied this principle for natural deduction to define basic data types such as bool and nav. We can explain the meaning of bool, we can define the meaning of a bool and nav using natural deduction. And in the definition of a nav, we also introduced this new element called primitive recursion. So we have applied this principle for natural deduction extensively so far to define logical connectives, first order quantifiers, and data types, general data types, and also basic data types. And the last example where we are going to apply natural deduction is predicates. Predicates on terms. So as a running example of predicate on terms that is defined with a natural deduction, let's use this less than. So now proposition A has is less than m, comma, n. So this LT of course stands for less than, and both m and n are terms of data type net. And we'd like to define this predicate less than using natural deduction. So what I mean by using natural deduction is, of course, we are going to have introduction rule for this judgment. So for example, we will have introduction rules of this form, less than and true in the conclusion. So if you read this rule top down, you end up introducing LT. So it's going to be some form of introduction rule. And just like the exercise that we had previously in defining NAT, here we designed introduction rules. So introduction rules were designed, and then we derived the elimination rules. Similarly here, we will design these introduction rules according to the meaning of this LT, or the intended meaning of this notion of less than. And then we will derive elimination rules from this introduction rule. So that's the plan. So to summarize, in addition to all these previous cases, we are now going to apply the principle of natural deduction to define predicates on terms. And we will use this predicate less than as a running example. And in the course of defining this new predicate, we will design these introduction rules and then try to derive corresponding elimination rules. So as you might have guessed, in Coq programming, you only provide introduction rules, and Coq will automatically derive these elimination rules. So let's do this. Uh, but I'd like to simplify the notation. So instead of LT mn, let me just write this m less than n. So this is a new form of a predicate. And here we assume n belongs to data type net, n belongs to data type net. All right, so the goal now is, now we have, in the set of propositions, we have this predicate m less than n. So what about the introduction rules? Internal rules. So internal rules specify when we can deduce m less than n true. That's what these introduction rules are about. So we can think of 4 combinations of terms m and n. 0, 0. So the first is m, the second is n. So we can think of 4 different combinations. 0, successor of something, which is successor of n. So let me remove this. And the third case is successor of m of, and the second one is 0. Finally, successor n and successor n. So let's go to each case one by one. So can we deduce 0 less than 0? And according to the intended meaning of this less than predicate, this should not be provable. We are in the middle of inspiring some interesting meaning into this symbol, this predicate. And we decided to disallow this judgment because that doesn't comply with the intuition that we have about this less than, the notion of less than. So we are not going to introduce an introduction rule corresponding to this case because this doesn't make a sense according to the intended meaning of this symbol. And what about this one? Yes, this is always true. So we introduce, so we have this new introduction rule, 0 less than successor n true. And this doesn't require further evidence because according to the meaning of natural numbers, 0 is always less than successor of something, or successor of something is always greater than 0. So you don't have to provide anything here at all. So let's call it less than introduction rule 0 case, and the premise is empty. And what about this case? Successor of something cannot be less than 0, so we are not going to have a corresponding introduction rule. Finally, in this case, sometimes successor n can be shown to be less than successor of n, but only if you can provide additional evidence, namely m is less than n. So if this is true, then this is also true. So let's call it less than introduction rule successor case. So now we have these 2 introduction rules. And notice that these 2 introduction rules decide the meaning of this particular predicate. There's no definition of this less than symbol. We give the definition of this symbol or this predicate, and the definition is fixed by these 2 introduction rules. In other words, these 2 introduction rules decide the meaning of this predicate. Now let's try to derive the elimination rules from these 2 introduction rules. So elimination rules. Remember that we are designing these introduction rules, but on the other hand, we will derive these elimination rules. So elimination rules start with an existing judgment, something like this. And then the question is, what kind of a new judgment can we extract out of this existing judgment? That's what this elimination rule is about. So again, let's consider four cases: 0 less than 0, and 0 less than successor of n, and successor m is less than 0. And finally, we have successor m is less than successor n. So the first case, according to these two introduction rules, this should not be provable. And similarly, this one is not provable because 0 cannot appear to the right-hand side of this less than. But these two guys are not provable. So if you had a proof of this one, it would mean that something terrible has happened. Because according to these two introduction rules, these two guys are not provable. So if you have something like m less than n, if you have something like m is less than 0 true, which covers these two cases, something terrible has happened. We have just proven something impossible to prove, so therefore we can prove anything. So this is less than elimination rule 0 case. It's similar to the elimination rule for bottom. If you have a bottom true, then you have just proven something impossible to prove, or the most challenging judgment to prove. Then you can prove anything else. This was the bottom elimination rule. So we have a similar situation here. We have just proven something impossible to prove, so therefore we can prove anything else. So this is the first elimination rule. We have derived this elimination rule. And what about this one? Suppose that we have 0 less than successor and true. What can we extract out of this existing judgment? And if we go back to the introduction rule, this judgment is precisely the conclusion of this judgment. But this judgment has no premise. So therefore, it turns out that this judgment is worth $0. So in terms of monetary value, it's worth 0. It's worth nothing. So therefore, even if you have this judgment, there's nothing interesting to extract out of this judgment. Because if you go back to this introduction rule, the premise is empty. So there's nothing to extract. So therefore, there's no elimination rule. And the situation is similar to the fact that there's no elimination rule for true. There's no true elimination rule. And that's because the introduction rule of top has an empty premise. So the situation is precisely the same. There's no way to eliminate it. So this is the first elimination rule, and there's no elimination rule of this form. What about this one? Suppose that we have an existing judgment. Successor m is less than successor n true. How can we eliminate it to deduce something else? We can extract something else according to this introduction rule. So according to this introduction rule, the only way to prove this judgment is by proving this one. So therefore, if you start with the judgment in the conclusion, then you can obtain this one. In some sense, you can invert this rule. So this rule allows us to deduce m is less than n true. So in other words, you can justify this elimination rule less than elimination rule successor case. You can justify this inference rule using this introduction rule. So to summarize, we have derived two elimination rules. To summarize, we started with these two introduction rules, and from these two introduction rules, we have derived this elimination rule and this elimination rule. So let me write them again here. So the introduction rule looks like 0 less than successor and true, and the premise is empty, and successor m is less than successor and true, provided that m is less than n. This is less than introduction rule successor case, and the elimination rule is if m is less than 0, then something terrible has happened, so we can prove anything. And if successor m is less than successor n true, we can basically invert this inference rule, so we can deduce m is less than n true. Because the only way to prove this judgment is by applying this inference rule in some sense. So this is less than elimination rule successor case.